This is going to be study vlog number 2. The goals for tonight are working on, or maybe not working on anything. It's for like my research group. I'm supposed to be, I guess the goal of the project is to develop a transformer model on chip. So you know how with typical, I guess, machine learning applications, or typical machine learning is performed on GPUs. GPUs are a type of processor that's pretty readily available. They were originally made for gaming, but have found their uses in AI, especially in transformers. But they're very general devices, and they're hyper specialized for matrix operations. In turn, there could be a different approach to designing these chips, especially for machine learning applications, say transformer models, and that's actually the focus of my research. It's designing a chip that emulates, or a chip that can run like a transformer model on it, like on chip. I'm assuming it'll just be like a systolic array with a couple of components added onto it. And then I'm going to be performing like aging simulations on it to see if it is possible for the security or integrity of the actual model that's on the chip. I don't remember what I was going to say, but like I just have to test that. And the goal is to publish in DAC, Design Automation Conference. It'd be pretty nice to get that done. Maybe another conference and then one journal. We'll see though, fingers crossed. And so I've got a meeting with my research collaborator at 7 p.m. today. I'm supposed to, I don't really have like work to do just yet. Like I'm not building a circuit or anything like that, but I will be looking at the current literature and trying to figure out where the gaps are in there. And so that's going to be the subject of today. I do have other stuff to do, like my homework for digital photo processing, but I really don't want to do it. It's like way too much, like, or maybe not way too much work, it's just way too far off from everything else. So I'm gonna hold that back for after my research meeting. So yeah, I'm going to be looking up papers tonight and just reading through them, I suppose. And you guys will just watch me do that. Putting on a song. Oh, I also paid my semester bill. 8 bands! That is crazy. But hopefully the graduate incentive scholarship is gonna hit. So it'll be maybe 4,000 instead, but I don't know. paper I'm reading right now. It's called Older and Wiser, The Marriage of Device Aging and Intellectual Property Protection of Deep Neural Networks. It's just talking about using like aging methods, like applying an excess amount of voltage to a specific part of the chip so that the weights on it get like messed up, and then you have like a fine-tuned like software that can like modify the weights at that specific point. Sorry, I can't focus with the music, but typical like GPUs and stuff, those use the von Neumann architecture, and so what they do is they call the weights from the memory, and then the weights go from the main memory, which is just like the like the SRAM. It's not SRAM, it's like DRAM. So, well, not even DRAM. It comes off of like the SSD to the DRAM, and then from the DRAM it goes to the caches, and then from the caches it goes to the actual main like processing elements. And so you have to keep calling them back and forth, back and forth, back and forth, because the cache isn't big enough to store all of the model weights. This neuromorphic computing stuff, really, it's just a bunch of like cascading arrays. So it's like you have an array, and in this array, you load in. It's like an array of SRAM, and SRAM is like a specific type of memory. It's like a DRAM. DRAM is made out of 2 transistors. SRAM is made out of 6, which is a lot. It's pretty expensive. Some people are trying to do it using like RAM or STT-RAM. That's what my lab's focuses on, using RAM. I don't think we'll be able to do STT-RAM because we don't have the money for it. But right now, this paper talks about the usage of SRAM in these like arrays, and how a lot of like machine learning applications work is that they use these arrays. They just do a bunch of like array calculations over and over again. It's just matrix multiplications again and again and again. And so if you have to build up this matrix piece by piece and then multiply it piece by piece, you're going to spend a lot of time. However, if you just put the whole matrix on a piece of equipment that's just made to hold the matrix, and then you just like multiply it by another matrix, or like overlay that same matrix with another matrix, then you like cut down on the speed immensely. And so that's what the goal is over here. And what they're doing is they're trying to prevent people from being able to read those weights that are stored on those SRAM cells. And the reason why they want to prevent that from happening is because if someone, this is a pretty grim example, but say you've got like a drone that has like a video camera on it, and there's a machine learning algorithm on there that can detect if there's like a US soldier or there's like a enemy combatant. And so a malicious actor, they can take the if they manage to get their hands on that drone, they may be able to steal the algorithm on there, and then by stealing that algorithm, they'll be able to know, hey, this is what the drone looks for to tell if it's an enemy combatant or if it's an ally. From there, they can actually, I guess, modify maybe how they appear themselves, or maybe they can even modify the drones themselves. Maybe they could upload a virus or something like that, I don't know. And by doing so, it could result in these drones being messed up, and anything could happen. Same case with like those Tesla, like auto driving, Waymos, all of that stuff. Someone could really mess it up. So the goal is to prevent people from stealing that data, or modifying that data too. So what this paper tries to do is they try to prevent that from happening by aging specific parts of the model itself, like the chip. Sorry for like the whole word vomit, but I think it's important to know all of the background information so that you can follow along with what's going on in this paper. So there's like this, they age it by applying like a certain amount of voltage over like a really fast time. So maybe they'll apply like a crazy amount of voltage in like I don't know, 24 hours, and that should actually age the silicon on the chip. And by, I guess, so what they do is applying this huge amount of voltage also causes like an increase in current flow. An increase in current flow means that more electrons are moving, they're bouncing around, all that stuff. And so eventually this heat will actually cause some of the bonds on the p-type transistors. So there's two types of transistors. There's a p-type and an n-type. Let's just say p-type are transistors made of silicon that are doped with column 3 elements. So that means that it's a 3-bond element attaching to a 4-bond element. And so you know that that's one element's, that's 1 bond fulfilled, 2 bonds fulfilled, 3 bonds fulfilled. But this 4th guy over here, he's lonely, so he's got like an extra electron to spare. And so that sort of leads to this like, I guess I don't even understand it all that well, like property that causes like positive charges to flow. Not necessarily, it's just positive charges flow because we're loaning a negative charge. Like we're losing a negative charge. And so the absence of a negative leads to that positive. Take it as like having -10, and see you have the number -10, and for some reason you drop down, you move up to -9. So that -9 is still more positive than -10. That's sort of how I like to think of it. It may not be accurate though. And so what they end up doing is, that's p-type. N-type, it's the 5th column, so there's like that extra electron that's going to be floating around. And so this electron is bound to that material. But when it's heated up, it causes like aging effects to occur, like NBTI. NBTI is when the bonds break down, so it causes like these electrons to move around or something like that, and that means that the silicon can't flip correctly. It takes too much time for it to accumulate charge, in turn causing like a bunch of different problems. However, what they try to do is they actually age it to a certain extent, and then they run some code on the chip that can like change the weights on the aged SRAM so that it comes out to be similar to the already existing model. And so far that's all I've understood from the paper. I haven't finished it yet. I've just got like the main page of the paper pulled up right now, or like I've got like I've read past the abstract, but I've just got the abstract opened up right now. I'm gonna get back to it though. I lost my main glasses, so I have to use my older nerd glasses. So I finished the paper, and what they decided to do was they only looked at the HCI aging rather than MBTI. And that's fine. They have like a pretty typical like experimental method, which is just testing it on like different types of models that already exist, like ResNet. I guess something that I'm not quite sure what they do is how do they how do they tell, like how can they detect if a chip has been aged or not? Because they show that it does work. um, if you age it to a certain degree, then um, there's going to be a huge difference. It's just I don't understand how they reflect the aging on the chip itself into the model that they've got. In order to like reflect that change, wouldn't it just lead to you having to still input that model onto your chip? So it's going to be just as easy to read it. Maybe I'm like misinterpreting it, but it seems like it doesn't really do much except just a test on aging and model accuracy. I'm struggling to see the security aspect of it. this paper. This is so lame. This dude's been on a roll. He's published like 3 papers to Nature and then 2 to Science in like 1 year. How do you even do that? Probably through international students. So right now, I'm just looking for papers that go over the effects of device aging on neuromorphic applications, particularly in the usage of deep neural networks, hopefully transformers, because that's like the goal. There's not a lot out there on transformers, so that'll be one topic to explore. And then I'm looking at types of hardware built that specifically works for transformers. As like a side project, I've been looking at like spiking neural networks, which are typically used in neuromorphic applications, but since neuromorphic applications aren't so like well developed or like an industry standard, they're not going to be using this anytime soon. The reason being that the already existing processes for manufacturing these chips are so well developed for this specific purpose that all those variations that come with this different architecture are going to be so much more pronounced. It's taken like billions and billions of dollars to get to where we are right now, so I guess switching pace and going on to a different type of memory unit like RAM instead of SRAM would cost billions of dollars. So I guess right now it's an academic project, but maybe in the future when it's given the opportunity to develop more and there's like actual sustainable results, we may see a shift. Doesn't matter though, at least in my perspective, because I'll still be able to get the necessary knowledge needed to go into the industry, if that's what I choose to do. Like, I'll learn about chip design, chip testing, chip aging, all of the cool stuff, um, because it still applies to different technologies. I guess using those softwares. I'll also be working on like machine learning, so it's not anything that's like, too far-fetched for it to be applicable anywhere else. Um, I think I'm going to wrap the video up now because I need to use my iPad to take notes, and I'm recording with my iPad. But I might upload another video to make up for this short one later this week. Thanks for watching, and I don't know, God be with you. Bye.